In the previous video, we saw the definition of vector space and a subspace, and with so many examples. Rn, it's subspaces, spaces of functions. And as we learned, it's sometimes harder to figure out whether a given subset of a function space is a subspace than with the same question for subsets of Rn. And it's not surprising because thinking of function subspaces as vector spaces is a new concept, and it takes some time to get used to it. But that's what linear algebra is designed to do. So in this video, we studied the notions of linear independence, spanning set, and basis in the context of general abstract vector spaces. In particular, we'll emphasize how these notions serve to give coordinates to those abstract vector spaces, like spaces of functional spaces, spaces of functions. And then this approach will allow us to pretend that these vector spaces are just like Rn. So let us recall the definition of a vector space. So an R vector space, or vector space over reals, is a set capital V equipped with a distinguished element 0 vector and two maps, addition and multiplication by scalar, which satisfy the following properties below. We discussed them in the previous video. So if V is a vector space, we say a subset W of V is a subspace if the following three statements are true. So the 0 vector is inside W. The sum of any two elements in W is in W. So it's closed under the addition, and it's also closed under the multiplication. So any scalar multiple of an element in W belongs to W. For instance, a subspace is itself a vector space. Now, let's look at another example. So last time we learned that functions from R to R form the vector space, and observed that polynomial functions form the subspace. And they also form a vector space. So following the notation of your book, we can write P in this math BB font in LaTeX for all polynomials, and P sub n, polynomials of degree at most n. So we can add them like this, as if you add in numbers. So you would sort of look at the coefficients, add coefficients in front of the same powers of x, multiply them by constant as usual using this multiplication. And of course, there's a 0 polynomial, which is just 0. So this is a vector space. Now let's recall the linear combinations and span. So given the vector space capital V and vectors little v1 through vn, and the constants or scalars c1 through cn in should be math bbr, we can name the element which is c1 v1 plus and so on plus cn vn inside V is said to be a linear combination of those vectors with coefficients c1 through cn. And the set of linear combinations of these vectors is the linear span of those vectors. Linear spans are subspaces. Now we can turn this around and ask, given a vector space V and collection of vectors v1, v2, etc., it could be infinite in fact, such that every element of capital V is a linear combination of those vectors vi. So in other words, we find a collection of vectors which span V. We'll call this collection a spanning set. So, okay, let's recall, does it span R2? Vector 0, 1? No, right, because it's only sort of one vector, which we should do. These two, they do, right? So every point in R2, every vector is a linear combination of these two vectors. 2, 3, 4, 5. Yes, right, because they're not collinear. And you can, using parallelogram rule, obtain any vector by linear combinations of these two. How about these two? No, because they're actually proportional to each other, right? So one is the factor of 2 multiple of the other. Now let's take 3 vectors. If you add another vector to this collection, then yes, right? Because so we can leave only one of those 2, say 2, 3. So for 6 will be just fact multiple of 2. And then if you add 1, 0, they will form, they will span R2. Okay, so same question about space of polynomials of degree at most 2, space P2. Take these 2 vectors, excuse me, these 2 polynomials, x3 plus 3x squared, x cubed plus 3x squared plus 3x plus 1, and x squared plus 3x plus 1, and x plus 1 and 1. Well, so the first one is not even in P2, right? It has a degree 3 monomial in it. Yeah, so the question is, it's not, so the answer is technically no, right? Because it goes beyond the set. Just polynomial 1, no, right? How about x? How about x squared? 1x, also no. What about x squared? But these 3, 1x and x squared, they yes, because every polynomial of degree at most 2 can be written as ax squared plus bx plus c, where a, b, and c are real numbers. So yeah, this set of vectors spans space P2. Now, how about this? Yes, also, right? So see, you have, well, you should express it using different linear combination. So it's 1, x plus 1, and then you can recognize that this is x plus 1 squared. So if you like, you can make a change of variables. X goes to x minus 1, and then you'll get back to the previous example. Okay, now how about these 3? Well, the answer is negative, and then we'll discuss it a bit later, but maybe you can try to make a guess. So look carefully at those coefficients. Like, is there anything odd about well, combinations of some of the coefficients? For example, how about the coefficients in front of x squared? What can you do about those? Now, what spans P, the set of all polynomials? Well, so clearly no finite set does so, because for every finite collection of the polynomials, they have some maximal degree, whereas the degree of P is not bounded, so they don't span P for any n. So there's an infinite set that spans P, all elements of P. So in sense, by construction, they all span P. But we can say, we can make slightly better statements. So set 1, x, x squared, etc. spans P. Because every polynomial is a linear combination of these of these vectors. Okay, now let's talk about linear independence. So vectors v1, v2, etc. in a vector space V are linearly independent if none is a linear combination of the others. So equivalently, only trivial linear combination is equal to 0, right? So if the linear combination sum ci vi is equal to 0, it forces all ci's to be equal to 0. And we've already seen examples of this with the vectors in Rn. Okay, so how about to have a single vector? So by construction, it's always linearly independent, right? Because in order to turn it to 0, you need to multiply it by 0 constant, unless the vector itself is 0. So then it's technically not independent. Yeah, so according to those axioms, there's anything by 0. So yeah, so it's just a detailed proof of the fact that one vector is always linearly independent, unless it's a 0 vector. Now, on the other hand, well, we can sort of have a scalar. You can multiply it like this. Yeah, so v has to be equal to 0. So kind of, well, let's go over this again. So suppose that v, sort of, let's use the, make the counterpositive argument, sort of make the contrary argument. So suppose that v is dependent, then there is a non-zero constant such that if you multiply it by a vector, that gives you 0. Now, if you divide by this constant, because it's non-zero, and using the axioms, we get that, well, 1 over a times 0 vector is equal to 0, right? And on the other hand, 1 over a, so it's like v is the same as 1 over a times av, which is 1 times v is equal to v. So v itself has to be equal to 0, but we assume that it's not. And yeah, we did this argument already for Rn. Okay, now let's talk about two vectors. The set v and w is linearly independent unless one vector is a multiple of another. Again, let's try to prove it using this, first assuming that the statement is false. So say that they're dependent and try to arrive to a contradiction. So if they are, then there are constants a and b, not both 0, such that av plus bw is equal to 0 vector. Now, if a is equal to 0, then bw is equal to 0 and b is not 0. And by the previous argument, by the previous statement, that implies that w has to be a 0 vector. Now, on the other hand, if a is not equal to 0, then we can use the vector space axioms and to rearrange the above equation into, you can divide by a. So v is equal to negative b over a times w, which means that the vectors are actually multiples of each other, right? So therefore, we arrive to a contradiction. Now, how about subset 1 x squared x to the 5? Are they linearly independent inside P5? Yes, they are, right? So any linear combination of this is only 0 when a, b, and c is equal to 0. Now, how about subset x plus 1 squared, x minus 1 squared, and x of P2? Pause if you need to try to answer this question. Well, turns out that you can come up with a linear combination which is actually non-trivial, which vanishes, right? When you open up the parentheses here, you have the cross products, which will combine into 4x. How about subset exponential to the x, exponential to the 2x of the space of functions? Yes, the answer is yes. So suppose one has a multiple of each other. So e to the x is equal to c to the 2x. And then, well, that implies that, c is equal to e to the negative x, which is not true because, it's not a constant, it depends on x. How about sine squared, sine x squared, cosine x squared, and 1? Well, no, because of the trigonometric identity that we all know very well. So they are linearly dependent. Another example, e to the x, e to the 2x, e to the 3x of the space of functions. Yes, they are. We've seen it before. Now, when we start talking about the differential equations, this will be this will be important, like those who will form a basis of solutions. But sort of the hint is that, so I mean, we won't have to do this later, but for right now, suppose that there are three constants a, b, and c, such that linear combination is equal to 0. Then if any coefficient is 0, then we can use the method from the last slide. So now let's take a derivative. Differentiate over x, we'll get this expression. A e to the x plus 2b e to the 2x plus 3c e to the 3x is equal to 0. And then we can subtract first equation from the second. We'll get this, that b e to the 2x plus 2c e to the 3x is equal to 0. And again, we can rearrange things around, which is a contradiction because b and c must be constants and not dependent on x. So it's like kind of, this will, like I said, this will be important in the second part of the course when we'll talk about different differential equations. Okay, now let's talk about bases. So a subset of V1, V2, and so on of vector space V is a basis of V if it is linearly independent and it spans V. So it's the same definition as in Rn. So a reminder, we have vectors with canonical bases 1, 0, 0, 0, 1, 0, and 0, 0, 1. is a basis of R3, and 1x squared is the basis of for P2, for the space of polynomials of degree at most 2, right? Because every polynomial is a linear combination of these three vectors. And they are all linearly independent, as we argued on the previous slides. Now, we can rewrite this definition in a different way. A subset V1, V2, and so on of a vector space V is a basis for V if there is one spanning and only one, that means linear independence, way to write any element V, little v inside big V as a linear combination of these vectors V sub I. So there is a unique way to represent this, to write a linear combination out of these vectors. So given a finite spanning set, Vi of V, one can find the basis by iteratively throwing out vectors in the linear span of the others. So this procedure does not change the linear span of the vectors because they still span at every step of the process. And on the other hand, it must terminate since the number of vectors decrease each time. And we can only terminate when the remaining vectors are linearly independent. So we already talked about this by studying the column spaces of a matrix. So take these four polynomials, x plus 1, x squared plus 2x plus 1, 4, 4x plus 3, and x squared. And let's find a basis which for whatever space they span. So we'll try to eliminate those vectors which are linearly dependent. Let's do a little bit of rewriting. So you see we have x plus 1 here as the first vector. So let's try to, and then there's x squared over there. So we can kind of try to combine this together like this. So x squared plus 2x plus 1 is equal to, well, we can kind of write it explicitly as the linear combination of x plus 1, x squared, and 4 over here with the coefficients 1, 2, and 1/4 respectively. So we can throw this vector out. So we're left with four vectors, x plus 1, 4, 4x plus 3, and x squared. And then we can do the same exercise with 4x plus 3, which is this linear combination of 4 and x plus 1. So we can throw that one out. And that leaves us with x plus 1, 4, and x squared. And they are, as you can see, linearly independent. Now let's talk about how these notions interact with linear transformations. Recall that if V and W are vector spaces, a function T from V to W is said to be a linear transformation if T of CV plus C prime V prime is equal to C times T of V plus C prime times T of V prime for all C and C prime in R and all V and V prime in V. Another review about one-to-one and onto maps. So a function f from x to y is said to be first onto or surjective if every element of y is the image of under the function f of at least one element of x, right? So there's at least one element, one or more inside x, which are mapped into every element of y. And it's called one-to-one or injective if every element of y is an image of at most one element of x, right? So no two elements are mapped into the same element in y. So for linear transformation T from Rm to Rn, we know that this is one-to-one if and only if the columns of the associated matrix are linearly independent, and onto if and only if the columns of the associated matrix span the codomain or the image. For set x, there's a function from x to itself which does nothing. It's the identity function. It maps fx to itself. And when big X is a vector space, then this id x is a linear transformation. Well, you can check if it's not clear. Now, when X is Rn, the matrix of id X is the identity matrix. Invertible functions. A function f from x to y is said to be invertible if there is another function which undoes it. So if there's a g from y to x such that the composition f with g is identity in x and g with f is an identity in y. And it's note the similarity between this definition and the definition of the invertible matrix. And so when those functions are linear and x and y are vector spaces, then we're asking the matrices to multiply to the identity matrix. And as with matrices, if f is an inverse, it's unique, and you write it as f to the power minus 1. A function is invertible if and only if it's one-to-one and onto. So proof, assume it's invertible, f from x to y, then it's onto, right? Because for every little y in big Y, we have f of inverse of y is equal to y. And it's one-to-one because for every x with such that f of x is equal to y, we have x is f inverse of f of x, which is f inverse of y. So there's only one such x. And conversely, assume that function f from x to y is one-to-one and onto. Then for any little y from y, there's a unique little x in big X, such that f of x is equal to y. So consider f inverse from y to x, which takes y into the unique x such that f of x is equal to y. And it's easy to check that this is an inverse. So the inverse of an invertible linear transformation is again linear, right? To prove it, take a transformation from v to w and then take the inverse and then see how this inverse works. So T inverse of C1 of W1 plus C2 W2 is equal to, so we create here, insert the TT inverse, which is the identity transformation, and here TT inverse, which is the identity transformation, and then sort of use the rules of linearity, right? So first we act with T inverse in W1 and W2, and then act with T on them, and we'll get this formula. So T inverse is linear. Isomorphism. Invertible linear transformations are also called isomorphisms. If there's an isomorphism f from V to W, we say that V and W are isomorphic vector spaces. Isomorphic vector spaces look the same to linear algebra. So albeit they can look completely different otherwise. So any question which you can be asked just in terms of operations which make sense in any vector space, they must have the same answer in both. And we'll use the isomorphism f to translate back and forth. So take an example, the following map between a set of space of polynomials of degree at most 2 to three-dimensional Euclidean space R3, which sends a polynomial ax squared plus bx plus c into the triple ABC. So you can see here that for the purposes of linear algebra, those spaces are the same because they obey the same operations. So we learn immediately that no collection of more than 3 vectors in P2 can ever be linearly independent because, well, the same question, it is rather obvious in R3. But for other purposes, of course, these two spaces, they look quite different, right? It doesn't make sense to solve an element for an element of R3 for X, or take its derivative, for example, or divide by it. Yeah, so. A linear transformation T from V to W is onto if and only if the image of a spanning set is a spanning set. It's not a theorem. So suppose a collection of vectors Vi of the span vector space V. And to say that T of Vi spans W means that any little w in big W is a linear combination of those T of Vi. So since T is onto, we can at least write W is equal to T of V for some little v in big V. So since those Vi span, we can write V is equal to sum over I, AI Vi, and then W is equal to T of V is equal to T of sum, T of this linear combination is always equal to linear combination sum AI of T of Vi, which means that it spans, and then for the converse, if the image of any collection of vectors in V span W, then by linearity, they must map onto W. If you need, take a moment to think it through. A linear transformation T from V to W is 1-to-1 if and only if the only element sent to 0 is 0. Here's the proof. So T is 1-to-1 if every element of W has at most one thing in V mapping to it. Now, if two things map to 0, then T is certainly not 1-to-1. So conversely, suppose that 0 is mapped only to 0, then T of V1 is equal to T of V2, or in other words, by linearity, 0 is equal to T of V1 minus T of V2 is equal to T of V1 minus V2, implies that V1 is equal to V2. So these are the same vectors. And yeah, we've seen this argument already for the matrix. A linear transformation T from V to W is 1-to-1 if and only if the image of linearly independent vectors are linearly independent. That's another statement. So take a linearly independent collection of vectors Vi. But assume that their images in W are not linearly independent. If so, we must have a linear combination, a non-trivial linear combination of those images, which is equal to 0. So by linearity, it works like this, and by linear independence, this sum of AI Vi is not equal to 0. But as we discussed in the previous proof, T is not 1-to-1 because of this, because it sends a non-zero vector to 0, which is a contradiction, which is an impossibility. Now, conversely, if T is not 1-to-1, there is some non-zero vector V with T of V is equal to 0, and thus the linearly independent set V is sent to the non-linearly independent set 0, which is again a contradiction.